Welcome back to the Foundry by Forge College. All right, let's jump right into today's explainer. In our last lesson on transaction ordering mechanisms and determinism, we figured out the actual mechanics of creating a single canonical order of transactions so our network validators don't completely lose their minds. But today, we're tackling the billion-dollar question. How does that deterministic pre-ordering actually save us precious time?
I mean, think about it. It's one thing to know how to organize transactions, right? But the real mystery we need to solve is why getting rid of that ambiguity suddenly puts the entire network into absolute hyperdrive. To figure that out, we've got to look under the hood and catch the exact moments where our time is literally being stolen from us.
So here's our blueprint for today. First, we'll look at the consensus assembly line. Second, 3 sources of delay. Third, the pre-ordering shortcut. Fourth, running the timing numbers. And finally, scaling under high contention.
All right, part 1, the consensus assembly line. Let's build a quick mental model.
Let's imagine a physical factory assembly line for a second. Think of incoming transactions as your raw parts. The validators are your floor workers, and a finalized block is the shiny finished product. Now, if the parts come barreling down the conveyor belt completely jumbled up, our workers basically have to smash the big red stop button, stare at each other, and argue over what gets built first. It's total chaos. But if those parts are pre-sorted, the assembly line just hums. The workers grab the next part and build, with absolutely zero drama.
Which brings us to part 2, 3 sources of delay. Where exactly is all our time going?
You see, without pre-ordering, validators get completely bottlenecked on bullet number 1, right here, ordering negotiation. They act like a stubbornly inefficient corporate committee trapped in an endless meeting, yelling, "Hey, I think transaction A goes first," while someone else is shouting, "No way, transaction B goes first." It's exhausting. Now, propagation latency is just the speed of the internet, and verification is just computer math. Those take time, for sure, but it's that endless negotiation that completely derails our timeline.
Moving into part 3, the pre-ordering shortcut, where we start shifting work earlier. So how do we cancel that super annoying committee meeting once and for all? Well, it's actually really simple. We just shift the ordering work earlier in the process. The block leader steps up and provides a definitive order right up front. Then, validators run a lightning-fast mathematical check, maybe using a sequence number or a hash. They confirm it follows the rules and instantly send their fast accept votes. Boom! Meeting canceled. We just bypassed the whole argument.
When we map it all out like this, you can clearly see how pre-ordering directly crushes each specific bottleneck. That messy negotiation completely vanishes. Leader reproposals drop to practically zero because the leader enforces a strict canonical tiebreak rule right at the door. Now, as we often see in the advanced tracks here at Forge College, there are always trade-offs. Propagation and verification still happen, of course, and the leader definitely has to work a bit harder. But those unpredictable, time-sucking arguments? Totally gone.
Okay, part 4, running the timing numbers. Let's get into some concrete examples.
I mean, abstract theory is great and all, but let's look at the hard data. A typical optimistic block round might take, say, 70 milliseconds from start to finish. But by eliminating that 25 millisecond argument phase and adding just a tiny bit of verification time back in, we drop the total down to 54 milliseconds. That is a massive 23% efficiency gain, literally just by skipping the bickering.
Let's trace that timeline step by step. At 0 milliseconds, the leader collects and sorts. By 5 milliseconds, they've computed a compact hash. At 12 milliseconds, it reaches the validators. They confirm and broadcast by 22, and finality hits at exactly 42 milliseconds flat. By cutting out all those negotiation round trips, we completely remove the jitter, that unpredictable bouncing back and forth that usually plagues consensus networks.
Finally, part 5, scaling under contention. Let's see what happens under a heavy load.
This baseline efficiency is super impressive when things are quiet, sure, but what happens during a highly anticipated NFT drop where thousands of transactions are fighting for the exact same state? Without pre-ordering, high conflict causes the network to argue, fail, and argue all over again. But with a strict tie-breaking rule at the leader level, the network never even enters those death spirals of negotiation. This means our latency savings actually multiply, getting bigger exactly when the network is under the most stress.
Now, naturally, making the leader do all this heavy-duty sorting up front creates much larger files to send across the network. To fix this, engineers use a really clever workaround called lazy fetch. Instead of sending the massive, heavy block of transactions all at once, the leader just sends a tiny, compact proof of the order first. Validators agree on that order instantly and then quietly fetch the heavy transaction bodies in the background, in parallel. It is brilliantly efficient.
Which leaves us with a final provocative thought. If determinism gives us this incredibly stable, low-latency engine that never gets bogged down in arguments, how do we use that ordered execution to absolutely maximize our transactions per second? Well, that is the next great puzzle. Head over to forge.college to explore our other courses and uncover the execution strategies that power the fastest networks in Web3. Thanks for joining me on this explainer, and keep building.